Okay, let's talk about IP protocol. IP protocol is basically the internet protocol. So it is like most important protocol for us. So basically in this chapter, we will learn datagram format. The IP packets are called datagram. So we will learn datagram format, like the header of the packets. We will learn fragmentation, IPv4 addressing, network address translation, and IPv6. Let's get started. Okay, basically this is the network layer. So routing protocols, path selection, uh, and other like RIP, OSPF, BGP. These are we will learn in chapter 5. So for chapter 4, we have IP protocol, like addressing conventions, datagram format, packet handling conventions. We will learn in a bit. And ICMP protocol, it's basically the network management protocol. I think we will learn that as well. So this is IP datagram format. We have a version field. This is 4-bit. Specify the version, like if this is IPv4 or IPv6. We have a header length. This is usually 20 bytes. The length of the header is usually 20 bytes, but if we use options, this can go up, so we keep the header length. We have type of service. Basically, this one shows like if the packet is like real-time datagrams, like voice over IP, or if it is non-real-time datagrams like FTP, file transfer, something like that. So this field is actually important as well. We have a length, like the datagram length field. It shows entire datagrams, like included the data part. So in theoretically, this can be like maximum, because this is 16 bits, it can be maximum, like any packets in IP protocol, it can be maximum 65,535. So bytes, because of the length is 16 bits. But the problem is most of the time datagrams will be 1500 bytes because of the Ethernet protocol. The maximum transmission unit of Ethernet is 1500 bytes. So if you are using Ethernet, and if you have more than if your datagram is larger than 1500 bytes, so you need to do the fragmentation. We will learn that. So the remaining part, we have, let's see, version number, header length, type of the service. Okay, before here, we have 16-bit identifier. Actually, IP protocol, like most of the packets, we don't use this field anymore. This field is just obsolete. So like 60, you can utilize these bits. You have also flag bits here. Most of the time we don't use flag bits as well. So these fields are like most of the time it's utilized, but different methods. We have fragment offset here. We will learn fragmentation. We have time to live. So time to live is basically the maximum number remaining hops. Each time when a router receives a packet, it decrements the time to live part. Remember traceroute, whenever we talk about traceroute. So by setting this time to live, for example, if you set this time to live 1, when you send the packet, the next router will reduce by 1, so the time to live will be 0. Even if you don't reach the packet, like even if you don't reach the end host, you cannot move that packet anymore. That's it. We have an upper layer. It shows if the packet is like, if it is TCP or UDP. We have, okay, here total datagram length. For fragmentation assembly, like I said, we will use this field, some of the field in flag bit, but this 16-bit identifier, we will not use that. So here we have 32-bit source IP address. This is like the first IP address, basically. The person who generated this packet. This one is 32-bit destination IP address. So basically it is your destination. We have options field here. So in usually options field, like we don't use options field, it is 0. But there are some methods, like for example, timestamp, record routes, and so on, different methods. You can use this options field. So by definition, you can use at most 40 bytes options field. 40 bytes. So if you don't have any options, your length, the header length will be 20 bytes. As you can see, each of them is 32 bits, 4 bytes, and we have 1, 2, 3, 4, 5 for sure fields. 5 multiplication by 4. So this part will be basically 20 bytes for all IP datagrams, regardless the type or anything. Always it will be minimum 20. But if you use the options field, let's say you utilize 40 bytes, so the packet header will be 60 bytes. Okay, let's see. Yeah, it shows like this. So okay, how much the overhead? Obviously 20 bytes are coming from TCP, 20 bytes minimum coming from IP. So we have basically 40 bytes plus application layer overhead, the size of the data. And also if you use the options field, in addition to this overhead, you also have options field overhead as well. So IP fragmentation reassembly. So basically, we are using network devices. These devices are like the routers. Routers, we learn how routers work. In a couple of chapters later, we will learn how link layer works, like the Ethernet protocol, Wi-Fi protocol, and different protocols. So these are all devices. So they have limitations. They cannot have like infinite number of resources. They are finite because they are just devices. So MTU, maximum transition unit. So each network links have maximum transition unit, largest possible link level frame. For example, if you are using Ethernet, you have 1500 bytes. Ethernet has if your packet is more than 1500, we will do fragmentation. So large IP datagrams divided, like the fragmented within like each router, one datagram becomes several datagrams, reassemble only at the final destination. IP header bits used to identify order related fragments. So let's say you are using Ethernet and you have 2000 bytes of datagram. Your datagram size is 2000 bytes. But you know that you cannot transmit this packet because you are using Ethernet. So your router basically divides the packet into, in this case, into two places. So basically it sends one packet, like the first part of the packet, and then remaining part of the packet as totally new packet. Because you keep the fragmentation numbers and flags, you know these two packets are together. So at the end, whenever the host receives that packet, it combines, reassembles the packet, and it acts like it received only one packet. This is the general idea of fragmentation. So let's say here we have one packet, but this is your MTU, this is large part, so you cannot transfer this packet over this link. So basically this router, for example, assume that this is not Ethernet and this is Ethernet. So you can, let's assume that you can transmit, you are using different system, different cable. So you transmit this packet here, large packet, but this router is connected with Ethernet. So it cannot transfer this one large datagram. So it has to divide this packet into 3 smaller datagrams and transmit each of them like this. And as you can see, this router doesn't deal with reassembly. It doesn't care because it is not the end host. So here, this router receives, still not dealing with the reassembly. Whenever the host receives, like the end host receives, now several datagrams you combine in the correct order and you receive the large datagram, basically. The important part is we do the reassembly at our computer, at our network cables. We don't do at our routers. This is the important part because like router has more important jobs to do. Like it doesn't have the job to combine these packets and it doesn't care. So in the application layer, you receive the packets, you know that you basically before getting the TCP part, like the transport layer part, you combine the packet at the end host. Here, as you can see, let's see it in an example. Let's assume that we have 4,000 byte datagrams and we are using Ethernet protocol. We are using Ethernet cable, basically. So this is one large datagram, 4,000, some ID, fragmentation is 0, offset is 0, because this is only one huge packet. So first, this is obvious that we need at least 3 smaller size fragments, right? Because if we had 2, the size will be basically 3,000 length, still not covering it. So if we use like 3, we can cover at most like 4,500. But obviously, like, okay, question. From here, like in this part of the video, just stop the video and try to answer yourself. So if you get the answer correct, good for you. If you don't worry, I will tell the answer right away. So, in order to, let's say, if you fragment 3, like if you fragment like this, 3, what is the maximum size that you can send? Like, what is the maximum byte number here? Is it 4,500 or less or more? Here is the question. Okay, so I assume that you stop the video and make a guess at this. Okay, if you guess 4,500, your answer is not correct. Because now this is your datagram size, right? But whenever you divide the packets into 3 packets, basically each of them will hold 20 bytes of IP header. So actually, with using like 1,500 length, this one only carry 1,480 bytes of the datagram. This one also carry the same amount, 1,480. This one, 1,020, and so on. So that's the main idea. Even though, and you can easily see that, as you can see, we are sending 4,040 bytes basically. Okay, this one shows 1,480 bytes data field. Okay, how fragments work. So the fragmentation offset value for the first fragment is always 0. So this offset, like these offsets are basically showing the position of the data. For example, because these packets are separately sended, maybe you receive the second packet before the first packet. Maybe you receive this one before the first packet. So we use this offset as the position of that fragment. The first packet starts from 0. So the field is 13 bits wide. So the offset can be from 0 to 8191. And fragments are specified in units of 8 bytes, which is why fragment length must be a multiple of 8. So here your data size is 1480. So if you divide this number to 8, you will receive 185. So here, that's why the offset is 185. You are dividing this number because this is the size of the data field in this packet. You are dividing this one by 8 by definition because fragments are specified in units of 8 bytes. So that's why you calculated this offset by 185. Here you sent another 1480 bytes data field, right? So from here to here, your offset needs to be incremented by 185. As you can see, this is 370. 0 to 185, 185 to 370. This is how we do the fragmentation and we do the reassembly in IP protocol. Okay, IPv4 addressing.